Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Garrett Levine with us today. Hello, Garrett.
Hi, thanks for having me on the show, Frank.
Well, thank you so much for agreeing to talk about your very awesome PSJ article here, which we'll get to. And Garrett, where are you located at?
I'm currently in New Haven, Connecticut. I'm at
Ooh.
Yale.
Okay. And how is the summer going in New Haven?
It's been hot and humid, although today we actually have a little bit of a reprieve. It's in the low 70s, which is nice.
Oh,
So I think we're
lovely.
starting to get into the nice time of year.
Fall approaches in the Northeast. Very good.
Yes, probably not for you, I'm guessing.
Yeah, it is August 24th.
Yeah.
2023 as we record this, and it is definitely not 70 in Phoenix. Oh no. Oh, we did get a little bit of we did get a couple days of cloud cover because of the Hurricane Hillary that came up to Baja and to San Diego. So we didn't get much rain. That was kind of a non-event for us, but we did get several days of cloud cover, and so it was a nice little reprieve. So
yeah, that's good.
Cool. And what's your position there in New Haven, Garrett?
I'm a graduate student in the astronomy department, so I'm just entering my fourth year now.
Oh, very good. So very soon I get to call you Dr. Garrett. That will be very
hopefully soon. Yeah, the end is closer than the beginning, so that's great. So
very cool. Very cool. And Garrett, what do you like to do for research?
I'm interested in planetary systems and their formation and evolution. Specifically, I guess I'm interested in kind of novel and creative tracers of said formation and evolution.
Cool.
So recently, or since coming into graduate school, I've done some work on interstellar objects and interstellar comets. Of course, we know of two of them thus far, Oumuamua and Borisov, but fortunately on kind of the time scale of the rest of graduate school, beginning of postdoc, the LSST is coming online, which should hopefully increase our population by a factor of 5 or so. So it's kind of an exciting time for someone like me to be going into this field and starting to think about what this completely new tracer of planetary systems can tell us.
Very cool. Very, very cool. And that is going to bring us to this awesome PSJ article. It's open access. It's the open access era, people. You can go grab a copy for free. Go get one. Who is right? Interstellar comets from post-main sequence systems as tracers of exosolar Oort comets. And Garrett, take us away.
Cool. Yeah, thanks for reading that. That's a little bit of a mouthful, so I'm glad you did it.
I can't believe I stumbled on main sequence.
So I kind of talked a little bit about the LSST, which is going to be this fantastic, wide, vast, deep survey, go a few magnitudes deeper than we've ever gone before for an all-sky survey. Lots of people are interested in it. Of course, we have all the dark matter, dark energy folks interested in it. And the solar system people are as well, for inventorying the solar system and potentially telling us about this kind of new class of objects, these interstellar interlopers that we have 2 of thus far. They have serendipitously passed through the solar system, but now with the LSST, we sort of expand our search volume by a factor of 10.
Nice.
And so the back of the envelope extrapolation would tell you that you'll go from 2 to 20 interstellar objects. And at that point, you can start to actually ask some interesting questions about what these objects are telling us about planetary systems. And so, of course, we can improve on these back of the envelope calculations. And so that's kind of the point of this paper, is to explore kind of a case study of what we might learn from the LSST. Cool. So I guess if you want to think about like where this paper came from or what kind of the spark was for this paper, it actually came from James Webb of all things, which was kind of interesting. I, like most astronomers in mid-2022, was kind of gawking at the photos and staring just kind of like mouth agape at like all of these images. And one of the ones that really resonated with me was actually this planetary nebula. I think it was like NGC 3132.
Very nice.
It's this dying star sort of in the last phases of its planetary nebula. And so it was just this gorgeous image with all of these, you can see all of the outflows and you can see the dust illuminated by the stellar remnant. And the thing that really was interesting to me, or the sort of spark in looking at that image, was looking at the size of the outflow and where that outflow was physically.
Okay.
And so just if you kind of like, I kind of remember looking at the angular size of the image and like holding up my like fingers to the screen and seeing that that outflow, where it was lit up, where that cavity was about 10 to the 4 AU from the star. And so that's interesting because that's actually, if there were an Oort cloud, all of those outflows would be passing through those comets. And so it could process the icy objects that might be stuck in that Oort cloud and could have been relics from the beginning of that solar system's history.
Yes.
And so that's really cool and interesting, and something that we don't have in our solar system, thankfully for us on Earth. And the other thing that struck me about that system is that we know it's very dynamically hot. It's very dynamically active because the star is shedding so much of its mass. So we see kind of the other side of this in polluted white dwarfs, where we have planetesimals accreting onto white dwarfs.
Right.
But the thought was that if you have this star that loses approximately half of its mass very quickly, and with respect to the orbital timescale of the objects, that should release those Oort cloud objects into the interstellar medium at the same time that they're being processed.
Cool.
So the hypothesis to kind of test, and what this case study is per se, it's just one case study of the kind of new science that LSST could open up, is could one of those pass through the solar system? And if it did, would we be able to distinguish it from its regular old main sequence counterparts?
Yeah.
Like the ones that we think our solar system ejected if in sort of an early instability type model.
Okay.
So that's kind of the impetus for this paper, kind of the motivation for this paper. It's not, of course, a complete look at all of the things that LSST could find, but it's kind of taking a end-to-end look at one of these such cases. So what we did is we kind of tried to tell the story of what these objects would look like. These objects had actually been considered in the context of Oumuamua because people were considering lots of hypotheses for Oumuamua.
Indeed.
And so Brad Hansen, Ben Zuckerman actually proposed this novel class of object called Jurids that would have been such objects. And of course, the statistics didn't quite work out. You wouldn't really expect one of these to pass through pan-stars. So this requires reevaluation in the LSST era, where we have an order of magnitude greater sensitivity.
Yes. Cool. I'm with you.
Great. Okay, cool. So that's so what we did in this paper is we looked at kind of the feasibility of ejecting these objects into the interstellar medium, and we did kind of confirm that they were ejected into the interstellar medium. We can actually scroll down to the in section 2 paragraph there, and I'll just give an overview of what we did before we get into it.
Yeah.
Right. So first, we kind of took a dynamical look at what these objects' ejection fractions would be. Do we expect the entire Oort cloud to come unbound? Do we expect less? Do we expect a small fraction of it to come unbound? Yeah. Sort of what is the fraction of converting these objects into interstellar comets?
Good.
And then what we looked at after that was looking at kind of the environmental conditions, those outflows that were in the NGC 3132 image, whether we would expect the comets to be processed in such a way that if we did see it, we would know it. Right. And so after that, then we actually looked at whether we would see such objects. So after figuring out that they would not have been destroyed in these outflows, which was an important question to ask.
Yes.
Yes. And figuring out that these things, if they did exist, would be in the interstellar medium floating around, we then developed a population model where we figured out what kinds of size frequency distributions could be there, and then how LSST would do at detecting objects from those size frequency distributions.
Yes.
So we're able to kind of propose testable predictions for the LSST, because we're able to connect these size frequency distributions to physical and chemical modeling, and then connect that to, of course, the underlying populations in the LSST sensitivity.
Very nice.
So that's kind of the overview here. It was really an interesting and fun paper to write. I've been interested in fast moving and small objects for quite a while. And I had a great bunch of co-authors who were on this paper who were able to really help with the paper, help just with fantastic scientific discussions. I wanted to actually shout out to both Astor Taylor and Devin Hoover, who were both graduate students at U Chicago when this was written, and are now or who are undergrads at U Chicago when this was written, and are now beginning graduate school. So Astor is beginning at the University of Michigan this fall, and Devin is beginning at Arizona LPL this fall. So just kind of down the road from you.
Good shout out. Good shout out.
So yeah, and then everyone else on the paper as well, Daryl and Rob and Jenny and Greg were also very awesome co-authors. I couldn't have asked for a better group of people to write this paper with. So yeah, hopefully you'll see big things from Astor and Devin soon as well, and maybe have them on the show down the road.
We'll do. We'll be on the lookout for that. Cool.
Yeah.
Let's dig in.
So, yeah, let's get into this. So I think figure one's probably a good place to start. So this is kind of, we can kind of tell this paper is telling the story of how these objects would be getting from their post-main sequence systems and into the solar system, where we could then see them passing through.
Okay.
And so if you think about the dynamics of ejecting these objects, you can imagine for now just the system of a test particle orbiting at some semi-major axis and a star, basically. And that star is losing mass. So this is actually kind of a classic, the variable mass two-body problem. It's been considered in the literature since the 60s. And it was actually has been mostly considered in the context of binary star systems, where one either goes supernova or loses a substantial fraction of its mass in a planetary nebula. And so the question is, what happens in those systems? Does the binary star become unbound? Does the semi-major axis expand? Does it decrease? And so there's a really rich analytic literature that did this, because this was, of course, in the 60s, before we could do computational models. And so one of the, or sort of the key parameter to think about how things happen is this adiabatic index. And that's really just by comparing the mass loss timescale to the orbital timescale of the object. So it's really at the basic or fundamental level, that's all this dimensionless quantity the adiabatic index is doing. And so at an adiabatic index of 1, these quantities are equal. And so in the adiabatic limit, where phi is much, much less than 1, you end up basically just expanding along similar ellipses, because the particle continues to go around the star a bunch of times as the star slowly loses mass as viewed from the particle. Now, of course, as you get further and further out into where a hypothetical Oort cloud would be, or at least 10 to the 3 AU, you see that the adiabatic index, according to these contours here, is getting much greater than 1. So in this case, the particle doesn't really get around the star on the time scale of the mass loss. It's, if you're hanging out at 10 to the 4 AU, you barely move. And to you, the planetary nebula looks like it happens instantaneously. And so in both the adiabatic limit and the very non-adiabatic limit, the impulsive regime, as you can say, there's actually some nice analytic approximations that you can do to tell you what happens to these objects, and to tell you what happens to the semi-major axis of these objects. So I think we can scroll over to figure 2 at this point.
Okay, I'm with you. Okay, eccentricity versus probability. Okay.
Yeah. So what we did is we took the sort of impulsive regime here, which is where the particle doesn't move, and it's almost like a supernova, where it happens instantaneously. In this case, it's a planetary nebula, but a few 10,000 years or 100,000 years versus instantaneous supernova doesn't really matter at these semi-major axes.
Agreed.
And so what we've plotted here is the results from the analytic model for the probability of ejection for a test particle on the y-axis, and the initial eccentricity, so the eccentricity before the mass loss happens, on the x-axis here. And so what we can see is for circular orbits, the probability of ejection, as long as the star loses more than half of its mass, is unity, right? And that's just because when we divide the instantaneous orbital velocity by the escape velocity, we get a factor of 2, so or root 2. So if the mass decreases by a factor of 2, then it's instantaneous ejection regardless of semi-major axis, as long as you're far enough away for that mass loss to look instantaneous.
Cool. Okay, I'm with you.
But then, of course, as you get more and more eccentric, then you have to compare where the particle is on its orbit to what the escape velocity is at the point where the particle is getting ejected or not getting ejected from. So, and what you can do, because it's a nice Keplerian orbit, is you can figure out what part of the ellipse the particle needs to be on, and it needs to be close to periastron in order for it to be ejected. Because if you're closer to periastron, you're moving more quickly, so therefore you get closer to escape velocity. And so what we did is we ran these calculations, and we plotted what the results from this analytic model were for 1 through 8 solar mass stars. And so that's the range of stellar masses that we're considering. And that's just because anything bigger than 8 solar masses goes supernova. Anything smaller than 1 solar mass probably doesn't have time to evolve off the main sequence during the galactic lifetime. So when we do population level things, we'll actually integrate over the initial mass function weighted by the stellar lifetime for this range of stellar masses. So that's kind of an important little aspect of the model, is that these are kind of intermediate mass stars is what we're probing. We're probing solar mass stars and up. Just because of the way the IMF is sloped, it ends up being mostly 1 and 2 solar mass stars, which is nice. So these are kind of solar analogs, maybe up to F stars and A stars, but we're really not getting too many, or the population is not getting too many of these 5 through 8 solar mass stars in it.
Okay.
So
very good. I am with you. Okay.
So yeah. So we can kind of validate the analytic model by doing the numerical modeling just by putting a bunch of test particles in orbit and initializing those test particles on a grid of eccentricity and semi-major axes. And so that's a good way for us to probe sort of the inner Oort cloud, where these where the adiabatic index is about unity, and it's less clear what happens. That figure 2 kind of breaks down. So what we can do is scroll down to figure 3.
Okay. Figure 3, and here we go with numerical. Okay.
Yeah. So this figure is really just
your grid,
probing the adiabatic index when it's close to unity. So we on the top y-axis or top x-axis there, you can see that the adiabatic index that we're running from is really 0.1 to 2. And so we're within the range being close to unity. And the heat map in the background is just the grid of objects, their fraction of objects that were ejected. So as we see for eccentric objects further away from the star, we get actually less and less objects getting ejected, because they have to be very, very close to periastron to get ejected with high eccentricity. And they just by Kepler's laws, they hang out at apoastron for most of the time. So most of them aren't going to get ejected. And then what we can see is the orange dotted line is just a prediction from the analytic model, where everything under that line should be white, where everything should get ejected under that dotted line. And that's what we see even at low adiabatic indices, or adiabatic indices close to unity.
Interesting.
So that's kind of interesting and kind of nice. Yeah, of course, as you get sort of inner Oort cloud inside of 1000 AU, that approximation starts to break
down.
So that would be kind of the edge of our solar system's Oort cloud. Of course, we know nothing about the Oort clouds of these extrasolar systems, so they could be sequestering objects there. But just for the purposes of this paper and for this initial case study, we had to just scale things from the solar system. So we just scaled up orbital periods of the Oort cloud from the solar system to orbital periods around those stars as well.
Yeah, all good. And a little shout out there to Rebound. That's what you did the in-body stuff with. Very good.
Yeah. Yes. Yeah. Rebound's been a really nice package to use. So it's pretty good.
Shout out to Rebound. Very good. I'm with you.
Yeah.
Cool.
Okay. Awesome. So I think that kind of wraps up the dynamics section, at least in the first part of the paper. You can say that, yeah, this section shows that the objects should, or some substantial fraction of them, should get ejected into the interstellar medium during typical sort of mass loss modes. Now, it's important to, one important distinction, especially kind of in the inner Oort cloud, is that we considered linear mass loss for lack of, we kind of considered a thermal pulse that all the mass was lost linearly. As you get far and far away, that doesn't really matter, right? Like the time scale of the planetary nebula and the thermal pulse is so short that it doesn't particularly matter. But as you get closer and closer in, then there have been some folks that have actually coupled like actual like MESA stellar evolution models with dynamical models. And so that's something that could be done as well to get a little bit better of a picture of what's happening. But for the purposes of this paper, that at sort of our order of magnitude feasibility case study analysis, we thought that a linear mass loss was probably appropriate.
Perfectly fine.
Yeah. Cool.
Yep, there's our linear mass loss. Okay, very good. Yep. Okay.
Cool. So we can probably move on to section 3 at this point. Since at this point we know that most of, let's call it 50%, it's of order 50% of the exo-Oort clouds, if they exist and they have like a structure that we think our solar system's Oort cloud does, gets ejected. And so that's kind of the takeaway from that section. So at this point, we can move into sort of what actually sparked my interest in writing this paper in the first place, and that's the exocomet processing, right? So that's what happens to these AC snowballs, rocky snowballs, dirty snowballs, whatever you call them, that are embedded in these stellar outflows, right? And so to me, this was really an interesting section, and kind of a, this is really important too, because you have to not only get these objects into the interstellar medium passing through the solar system, but you have to distinguish between them and Oumuamuas or Borisovs, which are not from this population, because we can show that they probably wouldn't have resulted from the processes that would be happening in post-main sequence systems. So we looked at a couple of different processes that might be happening. One of them is that the stars are just very luminous. So like AGB stars are 10 to the 4-ish times more luminous than the sun. And so that can actually heat up Oort clouds to temperatures that like Uranus and Neptune are experiencing, which is kind of interesting. So all of these icy objects that had been locked up in a reservoir for a giga-year or so are now all of a sudden being cooked at least to 50K or something like that. And so what we wanted to do was figure out how far this heat then would penetrate into the objects, right? So is it just going to be surface level stuff? Is it going to be all the way down deep into these objects? And so we're considering of order 100-meter sized objects, which is probably on this small end when compared to the solar system's Oort cloud objects, but the objects actually need to be that small in order for LSST to see them, as we'll see in a later section. But at this point, we can actually just do numerical modeling of just 1D heat equations, right? And so that's what we did. You can just see the heat equation right there. And then scrolling down to figures 4 and 5, those are kind of the results of what we did with these numerical models. So on figure 4, you can see this is kind of the result of a full heat numerical heat conduction model. So this is just what we have done is we have taken a stellar evolution track from the MIST database, and we have placed a comet at 1000 AU And we then ran the AGB phase. And so we have a luminosity or radiation bath set by the AGB phase luminosity. And then we figure out where the temperature, how deep the temperature gets, how deep the hot temperature gets in the comet. I didn't quite say that right, but how deep the heat wave penetrates.
Over the lifetime at which that heat source is present.
Yes, exactly. So over the lifetime of the post-main sequence, or of the AGB specifically, how deep does that heat wave get in the comet?
Okay.
And so what we showed is that even for some of these massive stars with the shortest AGB phase, the comet is basically thermalized to the effective temperature. Okay. So it doesn't really matter how deep it gets, because it gets all the way through the comet. And you can like just a simple like diffusion equation can also show you that as well, like a sort of dimensional analysis order of magnitude diffusion equation can show that as well. But we numerically confirmed it, which is nice. So
and what's the object of 86?
So 86K is the sublimation temperature that we assumed for CO2. Okay. So that's assuming if CO2, or if there's CO2 ice on this object and it can access the surface, then it should be gone.
Yes. And
so that's a sort of that's a testable prediction that we can make on the composition of these objects if we see them. Or it could be a more likely, instead of a testable prediction, it's more of a clue to the origin of such an interstellar interloper if we were to see one of these. Right. It could clue us in and say, hey, maybe this object was in a hot environment for some time.
Very cool. Okay, I'm with you. I'm good.
So yeah, so based on this figure here, where we showed that the numerical model shows the heat gets all the way through the object, then what we can do is we can actually just take the maximum effective temperature in the post-main sequence phase, and we can assume that that is the temperature at which the object gets to during the post-main sequence. So it saves us from running the entire grid of models that we would have had to run on figure 5. So just scrolling over.
Maximum during AGB phase. Okay.
Right. So this is showing, or with the result of figure 4, basically telling us that, yeah, the heat gets through the object. We can then say, okay, great. We can just take the maximum luminosity from the mist tracks for all of these objects, and then we can assume that that is the heat, or that is the temperature that gets all the way through the object.
Yes.
So now we show contours of assumed sublimation temperatures for H2O, CO2, CO, and H2. These are some ices that have been proposed. The 3 ices on the left have been found in solar system objects.
Yes.
And then, of course, H2 was the subject of a hypothesis about Oumuamua as well. So we showed that kind of for fun. And so what you can see here is that really, despite the higher luminosity of the star, it's really only CO is going to be what could get sublimated during the post-main sequence system. So, or during the post-main sequence. So if we see one of these interlopers that lacks CO, that could be telling us that it could have been from an inner Oort cloud type region if it were released and during the post-main sequence, and it has kinematics that look consistent with being drawn from the white dwarf population.
A stripped comet, if you like.
Yeah, something like that. So,
very good. Stripped comet. Very good.
Right.
Okay.
Yeah. So that's the sort of one point that I want to make about figure 5 here is, or the sublimation temperatures, is that sublimation from comets is very tricky. Figuring out temperatures at which things, quote unquote, sublimate is actually difficult, because the binding energies of ices can change based on whether they're embedded in a rocky matrix or what they're kind of.
Okay.
So it's a little. So these are not exact sublimation temperatures, but that's these are what we would call kind of representative values.
Fair enough.
So
fair enough. Good.
So, yeah. Um, so a couple of other effects that could be going on. One of them is these outflows are just could physically strip volatiles just because they're collisions with fast moving particles. So we actually showed that that probably wasn't happen or wouldn't happen in Oort clouds. There's just the amount of mass that impacts the comets is just not enough to strip the ices or to break apart the volatiles. If you just kind of compare the binding energy to the kinetic energy that impacts it from the outflows, that just doesn't really add up. And then the other thing that we considered then, if you scroll down a little bit to, I guess it's equation 21.
Let's do equation 20.
Kind of wrapping up this section here.
Mean free path, equation 21. We have the fraction that is covered.
Yeah. So even though it doesn't seem like the impacting outflowing material really does anything to strip the volatiles, it's interesting because AGB stars have all this dust that they're ejecting. That's what we're seeing in the JWST images. And so what we can show, or what we found, is that you can actually cover the comet with outflowing material. It's not very thick. It's only tens of layers of dust. But if that's something that could be detected from the Earth, or even if you were really ambitious and set an in situ mission to such an interloper, that could also be a clue that such an object, or that the interloper came from a post main sequence system. So I thought this was kind of interesting. Sorry, say that again.
ZW is the metallicity?
Metallicity of the wind, yeah, or the outflow material.
Okay. Yeah, I'll point it.
So just so just the amount of, it's basically just the amount of mass that hits
metals you got
the comet, and then you assume that the metals are the things that are sticking, or the metals are in the dust that's sticking. So that's
okay.
So we found that it could be tens of layers thick. So it's something. It's not like it's going to be completely covered in dust, and then that dust would be you wouldn't be able to like detect that dust in the solar system unless you had some in situ mission, or some like you were sensitive to what was on the surface with some spectrograph or something like that. But it's potentially another testable prediction as well.
Right. It's draped in dust.
Could be, yeah.
Thin layer of dust.
Cool.
Okay.
Very thin, yeah. Cool.
Okay.
So then moving on to kind of
how many are there?
The last little bit of the paper is sort of how many are there and how detectable are they? So section 4 is pretty straightforward. We pretty much just constructed, it just tells the reader how we constructed our size frequency distributions.
Okay.
So these, like many things in astronomy, are often parameterized by power laws.
Yeah.
We love us a good power law. And so we constructed these with power laws, and then we basically assumed, for lack of a better assumption, that the mass of the Oort cloud scaled as the estimated mass of the solar Oort cloud.
Okay.
Which is, call it 2 Earth masses or so.
Yeah.
That's plus or minus a factor of several. But for these purposes, we said 2 Earth masses was 2 Earth masses of stuff per
solar mass.
2 Earth masses of stuff per solar mass of star, of main sequence star.
That's good. All good. It's a good start.
So yeah, so that's actually probably a good enough discussion of section 4. We then discussed how many of them would be in the interstellar medium, just basically by integrating over the initial mass function times some factor that tells us how many of the stars for a given solar mass would have gone and become a white dwarf and potentially ejected these objects.
Okay.
So that, if you're good on section 4, that's actually probably good for me.
I'm good. I'm following.
I mean, it's power laws and integrating over the IMF and all that good stuff that is in most astronomers' toolkits.
Indeed.
So,
conditioning.
Yeah.
We can get into, let's talk about the total number. That's a good thing to talk about.
Sure, that works. Yeah, so then we showed, or we given all of these calculations here, we found the total mass that would be ejected from a star system per solar massive star. So this is just taking a solar-like star, and we can say, given the power loss slope of the SFD on the x-axis, how many total exocomets would be ejected on the y-axis. And so for each SFD, we have a minimum size object. This is just where the size frequency distribution starts. And so you can see kind of a turnover between 4 and 3 in the power loss slope. And all that really is telling us is that saying that for large power loss slopes, you start putting all of your mass in the smallest objects. And then for larger power laws, you start putting all of your mass in the biggest objects. So they start projecting very few things. So that's just that turnover in figure 7 there is what you're seeing there.
Very cool.
And so all of these sort of 10 to the 14-ish exocomets is starting to get to number densities that are interesting for the LSST. If you just figure out how many sort of objects per AU cubed, the number density that was inferred for Oumuamua-like objects is 0.1 per AU cubed. And so you can just, again, your back of the envelope LSST calculation should tell you that LSST should detect populations that are about 0.01 per AU cubed in terms of their number density. Now, of course, there's all these selection effects because of the LSST's cadence versus Pan-STARRS cadence. For these objects, because they're much faster than Oumuamua kinematically, you get a boost of a factor of a couple in the detection efficiency. But they're also fast moving, so they could streak across the LSST's image, and you could experience what's called trailing loss. This is just where you have a fast moving object that deposits its flux across a bunch of pixels instead of just one pixel. So it just blends into the background and you miss these objects.
Explicitly take it out as a streak.
Right. Or you think it's a satellite or cosmic ray. Something sad like that.
Something not interesting.
right, exactly. So there's all these sort of complicated selection effects that the LSST or any wide field survey is going to be confronted with when you start to look for these objects. And that especially comes true for these, again, small objects and these fast moving objects. So we built a couple of models of the LSST to kind of compare models and to test and see how detectable we thought these populations would be given figure 7. And so we kind of, in the way that we told the story in the paper, we kind of ordered these models from least complex to most complex. So in model 1, we just have we say that the LSST is looking at a quarter sphere. And then we calculate the angular velocities of the objects for a given size in that quarter sphere. And then we say if it's moving faster than the LSST's stated sort of where you start to lose things due to streaks, we just say it didn't see it. Otherwise, we say that it's seen if it's in this quarter sphere. So that's the sort of bare bones simplest model that you can construct, but it's a starting point. Then as you get to a little bit more complicated models, you can actually just numerically integrate the search volume. So you can take that quarter sphere, or you can take the field of regard of LSST, divide it up into a bunch of cells, and then you can just, for every cell, you can say, what is the limiting absolute magnitude in this cell? What is the What is the smallest object that I can see in this cell? Of course, still accounting for the streaks and your trailing losses.
Yeah.
So this is a little bit more complex than just like a quarter sphere given a typical phase angle of these objects.
Okay.
But again, it's still pretty simple and pretty straightforward to do and understand.
Good. One step at a time.
Yeah. And then our third model, this was a contribution from Devin, who is an undergrad, and this was part of his, I believe, part of his senior thesis work.
Wow.
From UChicago, is he wrote a paper previously that modeled the number of Oumuamua-like objects that could be detectable by the LSST. It took their trajectories, it numerically resolved those trajectories in one-day time steps, and then ran a representative LSST-like survey volume with those trajectories and found how many Oumuamua-like objects LSST would find.
Good. Okay.
And so for this paper, Devin actually reran that model, but with white dwarf kinematics instead of Oumuamua-like kinematics, thin disk kinematics.
Okay.
To see what kind of velocity boost we would be, or what kind of detection boost we would expect from the white dwarf kinematics.
Yeah.
And so if you look at figure 8, that's comparing all of these models here. And the bottom figure of that is just showing what the LSST's search volume is. And because of the way that we've treated trailing losses differently, these things really diverge around 60 meter objects. And that's just because each of those 3 models treats trailing losses differently and calculates the search volume differently. But as you get to 80-ish meter objects, they start to converge to within a factor of 10. And so as you start to get to even bigger objects, they start to converge even more, which is nice. And that's as expected. Sort of the asymptotic behavior is to start looking like the same model, or to start looking like the same detection efficiency.
Good. Okay. Okay. And the dotted line at a little over 100?
That is the Oumuamua-ish size.
Okay.
So yeah. Cool. Now, yeah, that's the Oumuamua reference size, assuming a asteroid like albedo. So,
yeah.
So of course, for all these things, right, there's the albedo effect, which is probably of order a factor of a few.
Yes.
And so what we're really interested in is actually the x-axis, the bottom x-axis, which is the absolute magnitude. So we're generally looking at things as a function of their absolute magnitude, which is a little, it's basically kind of just the geometry that you can't actually realize of what would this object look like as viewed from the sun. So if you're sitting at the center of the sun, how bright is it from 1 AU away? So if you put this object at Earth and you were sitting in the sun, how bright is that object? So it's a little different than absolute magnitude for like stellar astrophysics, but that's because these objects are much dimmer than stars.
Yes.
So
yes.
Yeah.
Would what sort of LSSTs? If I had to draw another line for LSST, where might that be?
So these are our
all of it.
Yeah. So these are our different models of the LSST search volume. So there is now an LSST, or there is in development, I believe, an LSST survey simulator. So that's coming out as well pretty soon, which will be great.
Okay.
Cool.
Good.
So yeah. So at this point, we now have a search volume, which is in AU cubed, and we have number densities in the solar neighborhood, which are in AU to the -3. So the nice thing is that if we just multiply those together, we get the number of objects that LSST should see at a given size, or at or larger than a certain size during the 10-year survey, which is great. So the reason that we cast figure 8 in total search volume is just because it makes that calculation really easy. So we just multiply we multiply the numbers together.
Okay.
So figures 9 and 10 kind of tell us the results of that.
Okay, 9 and 10. Let's start with Get a little global. Okay,
Yeah.
let's do 9.
Okay. Or I was going to say you can actually just look at both figures together. Might actually be the best way to do it.
Okay, we'll do that.
So figure 9 is telling us the cumulative number of objects detected smaller than a certain radius. So this is just basically almost a CDF, but the y-axis here is just the cumulative number discovered versus the exocomet size. If we just express these in terms of all of these lines are just different power law slopes.
Yeah.
So of course, for steep power laws, where all of the stuff is in the smallest objects, 60 meters is still large enough that LSST isn't too affected by trailing losses.
Okay.
So you see more and more objects for steeper power law slopes.
Right.
And then for shallower power law slopes, of course, you see less and less. So it's worth pointing out that the solar system is probably like Q is -3 or 3.5. So the solar system is putting a lot of its mass in larger objects. And so that's important because this figure is telling us that if exo-Oort clouds look like what we think the solar system's Oort cloud looks like, then we probably won't see any of these objects just because there aren't enough 60-meter objects. If you sequester all of your mass in kilometer scale or larger objects, then there's just not enough of them for the LSST to see them.
Okay.
And so this is a little discouraging, but it's also worth pointing out that the interstellar objects that we've seen thus far have been pretty small. They've been smaller than what we expected to find for interstellar objects. If you look at kind of the pre-Oumuamua literature on how good is Pan-STARRS at detecting interstellar comets, the assumptions were all kilometer scale or even larger interlopers, but now it's worth at least considering 100-meter interlopers, or 100-meter interlopers are what we have seen thus far.
That's right.
So, So then if you look at figure 10 is kind of it's a heat map of expected LSST discoveries for, again, these power law slopes on the x-axis this time, and objects size on the y-axis now. And each of those grid cells, you can think about it, is basically the cumulative number, so the y-axis of figure 9.
Yes.
Figure 9 is just showing you a cross-section, basically, or a single line through figure 10.
Right.
So that's why I wanted to zoom out so we can kind of interpret these together.
Got it.
So if you just take a cross section at minimum object size of 60 meters in figure 10 there, then figure 9 is really just showing you what that looks like.
Yes. Okay. Slice.
What that looks like it's a slice. Yeah, exactly. So as we can see, it's for. Yeah. So as we can see for any reasonable or for any solar system like parameters, you're just not going to see any of these post-main sequence comets, but which is sad. But if you kind of consider the steepest power law slopes, so call it just steep power laws that are basically just saying, in this case, like 60 meters is your representative size, or 80 meters is your representative size. When your power law slope is 6, you basically have all of your objects at the smallest size. And so the way to interpret figure 10 is that if we see something from a post-main sequence system, then all of the objects have to be that small. It's like you really can't have any of your mass budget in big stuff. Otherwise, it would eat up everything and you wouldn't be able to see anything with the LSST. So it would tell us that if we do see something that looks like it's kinematically hot, it was maybe drawn from the white dwarf population. Of course, that overlaps a lot with the thin disk population. So drawing one object, you probably can't really tell. But if it has the right kinematics and the right chemical composition, then it could be from a post-main sequence system. And in that case, it would be really remarkable because the exo-Oort clouds would look much different than our own solar system.
Yeah, right.
And so that's kind of what figure 10 is telling us, is kind of the big takeaway here, is that If we do see one of these, it would be strange and it would be different than our own solar system. But of course, that, of course, not unprecedented size because of Oumuamua.
Wow. We've been surprised
So
before.
we have been surprised before. So I guess I would say that it is not infeasible just because of the way that the LSST is set up, and our sort of what little we do know about Oort clouds is it's probably pretty unlikely, but it's not infeasible that if these populations do exist, we could detect it.
Nice.
So yeah, we can sort of, for the rest of the paper, for the last couple of pages here, we talked about if we do see one of these objects, what we would learn in terms of the occurrence of Oort clouds around these kind of intermediate mass stars. We talked about the fact that we believe that the Oort cloud in the solar system is a product of us having giant planets. And so that would tell us that giant planets are probably prevalent around stars for which it's difficult to probe for giant planets.
Yeah. Even as you point out here, even a non-detection is telling you something.
Right. Yeah. So a non-detection would probably tell us either that there's not a lot of stuff in exo-Oort clouds, or it's sequestered in big stuff.
Right.
So it's all kilometer scale or much larger than kilometer scale.
Cool. We got.
Yeah. So I think I kind of skipped ahead a little bit, or gave a little bit of a I kind of gave a summary of what we talked about in the discussion section. I'll just kind of point out figure 11 because it is the last figure of the paper.
Yeah.
It's just kind of the classic mass period diagram of exoplanets. And then in the background here, we've shaded them according to the log of their Safronov number. So any Safronov numbers greater than 1 can do the ejecting of the objects, or in our case, can impart objects into the exo-Oort clouds.
Right.
So really, what we would learn about exoplanetary systems from interstellar objects in general, not just these post-main sequence comets, is we would be learning about the presence of the cool colored planets here, these giant planets at large semi-major axes.
Right.
So hot Jupiters can't throw anything out of the system, at least not at their present semi-major axes. And neither can all of those Kepler multis, the Ps and the pod planets. They can't really do any throwing out of interstellar comets anyways. So yeah, so this is kind of just showing us the parameter space that LSST, by probing the interstellar comet population, is going to tell us about these cold giant planets. So that kind of takes us back to the sort of broader perspective of what we'll learn with LSST about planet formation. It's really these cold, distant planets.
Cool. And I will say that there is a pair of appendices that you may want to check out when you get there. You can check out some of the details of those dynamical models. Very nice. Very cool. Garrett, thank you so much for walking us through your very lovely article.
Yeah, thank you for having me on the show.
Yeah, really nice work. Very good. You touched on it a little bit during the talk, so let me push on it a little bit here. And where do you think we go given this analysis? Is it worthwhile going into more sophisticated theoretical models, or should we wait till the LSST simulation tool, or other telescopes might be able to pick it up? So just sort of next steps on this. Where do we go?
Yeah. So I think the thing that I would want to emphasize is that, well, so LSST's observational constraints are really going to be the most important thing for learning about the interstellar comet reservoir. It's probably, I think, detections or non-detections will be exciting. And that's kind of, LSST is the first survey for which either a detection or a non-detection would be exciting. And for interstellar objects in general, not just this specific population. I think this study is really a sort of case study, or it's one very small subset of what we expect to be out there. We do, of course, expect exo-Oort clouds to eject their objects. It just seems unlikely that the LSST might find one.
Okay.
Just because the population is probably still too small for LSST.
Yeah.
But there are populations of, call it Oumuamua-like objects, Borisov-like objects with brightness boosting tails that could be detectable by the LSST. And so I think it's important that in the meantime, we, especially us theorists, kind of prepare for what is to come and figure out what kinds of observations we want to make when those objects do appear, and how to really interpret what we see with the LSST. So I think it's kind of a combination of theoretical and observational work is what's next.
Awesome. Awesome. Well, I really look forward to seeing this topic develop, especially once LSST comes online and we start moving.
Yeah.
It'll be very cool to see what happens. Very exciting times. Very nice. Garrett, thank you so much once again.
Awesome. Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.